Hello, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on Polymer Modification Part 1, Fillers and Reinforcements. My name is Sherry Cutt, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your day to learn about polymer modifications as they pertain to plastics. A few housekeeping items before we begin, just so that you know, everyone except the presenter, Andrea, is on mute and will be on mute for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the question section of your toolbar. If you would rather ask your question verbally, please raise your hand and I will unmute you and call on you to ask your question out loud. In addition to our presenter, Andrea Kendrick, who I will introduce here in just a moment, we also have Andy Conti, Technical Development Engineer, on hand to answer your questions today. If your question does not get answered right away, we will address it at the end of the webinar. You can access and download PDF copies of Andrea's presentation, our product line card, and information on our technical engineering team in the handout section during the presentation. The presentation itself will not be emailed, so if you'd like a copy, please download it from the handout section before the webinar concludes. A certificate of completion and recording of the webinar will be emailed to you about an hour after the webinar concludes. We would greatly appreciate it if you complete a survey at the end of the webinar so we can improve future ones for you and cover the topics that interest you most. Andrea, if you want to flip to the next slide. We encourage you to check out our blogs. And let me see here. We encourage you to check out past webinars and recordings on the webinars page of our website. While our next webinar is not yet scheduled, once it is, the registration details will be listed on this page and on our social media sites. Andrea, go ahead and flip to the next one. I think it might be on the next slide about webinars.
Next one's about me.
Okay, nope, we missed that one. Sorry, guys. Anyways, like I said, you can go to our webinars page of our, if you look under chaseplastics.com/resources, you'll see our webinars and our blog listed there as well. If you would like a custom Chase to Knowledge presentation given to your presentation discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick. Our entire technical team is on hand to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. And another great technical resource here is our Chase to Knowledge blogs. This is also on our website. We currently have 4 topics live, and they can be found at chaseplastics.com/blogs. Excuse me. So at this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical development engineer with Chase Plastics and has been with us for 6 years. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase to Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise she brings to the table. Without further ado, Andrea.
Good afternoon, everybody. This is Andrea. Let's go ahead and get started on Polymer Modification Part 1, Fillers and Reinforcements. We call it Part 1 because I believe that we're going to probably do a few more that cover other modifications, maybe other additives or other fillers and reinforcements that aren't covered today. These are kind of, the basic ones that you see most commonly, and then potentially we'll talk about other ones in future webinars that might be of interest as well. So our agenda for today, we're going to go over what polymer modification is, what that means. We're going to talk about different fibers and fillers. We're going to talk about the effects on properties. We're going to review some of the properties. When we get there, you'll kind of notice their slides that if you had been into the datasheet presentation in the past, they mimic that. Just a nice refresher on those properties. Then we're going to talk about fiber and filler properties specifically. We're going to talk about some of the examples of how they're affecting the properties with some nice visuals to kind of give you an idea of what we're looking at. We're also talking about some things to consider or kind of keep in mind when we're talking fillers and fibers. And then we're going to talk about just a couple examples of some products that have been made utilizing fibers and fillers in them. So polymer modification, what does that mean? It basically means we're expanding the use of plastics in application by offering increased variety of property combinations. So how do we do that? We do it by either reinforcing the material, so either using fibers or fillers as reinforcements, using specific additives, maybe like an impact modification or a flame retardant package. Those would be examples of other additives that have been used, or also doing blends or copolymers of materials. So instead of using a straight PC or an ABS, maybe we use a blend PC-ABS to get a combination of the properties that we're looking for out of that. And then copolymers would be something like your homopolymer propylene. Maybe you utilize a copolymer for a little bit better impact, a little bit better flexibility. So today we're talking specifically about fibers and fillers for modification. So what are those different fibers? Today we're going to talk about standard glass. So when you hear a glass-filled product, this is generally what they're referring to. We're also about milled glass a little bit. We're going to talk about long glass fiber and then carbon fiber as well. We'll talk briefly about that. And then for fillers, some of the fillers that we're going to discuss today, we're going to briefly touch on glass bead, and then we're going to focus more on the mineral fillers, which are going to be your talcs, your mica, wollastonite, and calcium carbonate. So quick little table to give you an idea of kind of the properties and how that's affected. So these are general. There are an occasional rule of thumb or caveat to that, but in generally speaking, fibers and fillers affect properties in these ways. So your ultimate tensile strength or stress, you're going to see that fibers are going to increase that quite a bit. Your fillers might increase it a little bit. Your strain or elongation is going to be decreased with fibers and fillers. Your toughness and impact, this is where there's a little bit of a caveat, and we'll talk about it, but generally speaking, it does tend to decrease it a little bit. Your heat distortion temperature or DTUL, deflection temperature under load, if you're used to the old verbiage, is going to increase with your fibers. And then it increases a little bit with your fillers. It's more drastic with your fibers. Then your coefficient of linear thermal expansion, again, these are properties we're going to kind of talk about if you're not familiar with them. You'll see a little bit of a reduction with fiber usage, and then not much of an effect for fillers because of the way that they're shaped, and we'll get into that a little bit as well. And then for shrinkage, we're looking at an anisotropic shrinkage. So it's going to be different in different directions. Again, we'll talk about that a little bit more, but you're going to see that with your fiber reinforcement. And then with your fillers, it's more isotropic or more uniform in each direction. So now we're going to kind of get into the properties just a little bit. So if you're not familiar with these particular properties of the material, when we talk about how the fiber or filler has an effect on it, you kind of understand what we're talking about. And so again, if you watched my data sheet, shameless plug, the data sheet presentation, these were talked about as well. So tensile stress or tensile strength, if you hear it that way, is going to be basically how much force we can pull in opposite directions to get the material to break. And so it's tested either at yield, where the strain does not increase with an increase in stress, or tested till break. You might also sometimes see ultimate, which is going to be the highest value of strength that it resisted. And so these values are typically given in PSI or MPa. And then down here, you see kind of a little picture of it pulling a tensile bar in tension to do that test. So when we see the values, this is what we're looking at. You have tensile strain, also called the elongation. It's basically the measure of change in size versus the original size of the material after pulling it. So same test, it's done in the same machine. You pull the tensile bar in opposite directions, and then it gives you that measurement. So kind of an example of what that looks like. So paper, if you pull on the ends of it, really low elongation, it's going to rip, it's going to split, it's not going to stretch very far. Where if you take something like a Laffy Taffy candy, kind of pull it, it elongates quite a bit. So kind of a nice visual for you on what that looks like. And then we talk about toughness. I did just grab IZOD on this. There's also Sharpie testing and there's other impact testing as well, but I did just grab IZOD as a quick reference for it. But essentially it's the energy used to break a specimen under a flexural impact. And so I'm not going to read through all of this. If you guys download, the PDF, you can look at it. But essentially what that looks like is you have a force that comes down and hits it, it impacts it, and it takes that measurement of that material and how much it kind of resists being impacted like that. HDT, we're going to talk about a little bit as well because it is a property greatly affected by the fiber reinforcement, a little bit by filler. So heat deflection is going to be the temperature at which a test specimen is going to deflect 10,000ths of an inch when it's put into a load. So you can see kind of in the picture, the load is pushing down, the bar is being held, and then once it deflects a certain amount, it takes a measurement of that temperature. So this is actually kind of, it's a good test to use as a short-term heat resistance. So kind of just give you an idea where the material will perform. And then CLTE, I did bring it up, so I didn't want to put it on here as a quick reference material for you guys again, something that you can come back to and read through later. We don't have to go through it crazy. The thing to remember though is it really has to do with the change in length per unit length of a material when there's a change in temperature. So what does that mean? It means as we're outside and it's really cold here in Michigan and snowing, it's going to kind of shrink in a little bit and then it's going to expand as it gets hotter. And so we're talking, get to the summer months and now it's expanded quite a bit. So the reason we want to know something like that is that amount of change has a lot to do with if we're going to make assemblies or parts that it's going to come in contact with other materials. We want to know what that's going to look like, because if we're over molding it or we're attached to something like a metal and it changes more than the material does, it could potentially cause an issue. So the greatest example of this would be your PVC siding on your house. You overlap it so that way when it gets hot or contracts and moves either way depending on the temperature, it doesn't expose the side of the house. So again, just something to keep in mind. We talked about it. The fiber reinforcement is going to lower this value, so it's not going to move as much across the temperatures. So I did want to bring that up. And then shrinkage. Shrinkage is going to be a big one here. We are going to talk about it quite a bit. So shrinkage, if you're not familiar, it really is the dimensional difference between the molded part and then the actual mold dimensions as a result of the polymer chains contracting upon cooling. So when we go to process the material, we heat it up, it expands, and then in the mold, when we're cooling it down, it contracts back down. So that's going to be your shrinkage. And the thing to point out here is that all plastics are going to shrink. Now, how much they shrink is affected by the type of material. So if you're looking at a semi-crystalline material, they're going to shrink a lot more because they expand a lot more compared to an amorphous material like an ABS or PC. And then also we'll talk about how the fibers and fillers are going to affect that a little bit. And then another note here just to keep in mind, shrinkage on data sheets, great guidelines, good idea to kind of give you an idea where we're at, but do keep in mind that other things like your processing and your design could affect it. So just wanted to bring that up as well. So shrinkage, we tend to have values, especially if they're isotropic, just one value because it's gonna be the same in all directions. But what we really wanna focus on here is your anisotropic shrinkage or shrinkage that's gonna be different in different directions. So if you look kind of over here on the right-hand side, there's a couple little pictures that show you the difference. And so what I wanna focus on here is that you have your gate location on your part, and then you're gonna have what's called the flow direction, and then you're gonna have what's called the transverse direction or cross flow, depending on how you look at it on a data sheet. So for a normal part or a normal material, generally speaking, it's gonna be pretty isotropic. Both directions are gonna shrink pretty similarly for the most part. Semi-crystallines do tend to lean a little bit more towards potentially being anisotropic just inherently, but for the most part, fairly similar. Now what happens is when we do things like add in glass fiber, the glass fiber will start to orient in the direction of flow. A good analogy I've always taught or thought of is if you think of throwing a log into a river, the river as it's flowing is going to get the log to align up with the direction that it's flowing. So same concept. Your glass is going to do the same thing. It's going to align with the direction of flow. And so this is what causes you to have issues, or maybe not issues if you've planned for it, but it causes it to shrink differently in different directions. So what does that look like? That would be these pictures down here. So these are going to be in the flow direction. You can see how they're starting to align up with the direction of flow, and then your cross flow. And so it's going to be different in different directions. So that's going to be the one big thing that we talk about when we talk about fibers affecting the material and the anisotropic shrinkage. Okay, so now we want to talk about the different versions, or I kind of already brought up the different ones we were to talk about. So now this just gives you a little more data, a little more information on these particular fibers. And so in general, when we're talking about fibers, they help boost your mechanical properties, so your stiffness and strength, as well as your thermal properties, so your HDT that we kind of talked about a little bit. So the main ones here being your standard glass. And so typical loading anywhere from 5 to 60%, depending on what you're trying to achieve or what you're doing. Typical diameter and length. So you kind of notice that they are a little different We will talk about what's called an aspect ratio on the next slide, which is what causes some of these things like it to align and the anisotropic shrinkage. The other thing to note here is colorability. So you'll notice that it's yes across the board until we get to the carbon fiber, and we'll talk about that a little bit. But relative costs we're looking at, this is kind of comparing those 4 different versions. When we're talking about relative costs compared to maybe fillers, a little bit different, but this is relative to what we're talking about fiber specifically. And so your standard glass is going to be a standard length, 3 to 20 micron, 3 to 12 millimeter in length. Then we move to what's called milled glass, and essentially it's kind of like a shorter version of it. So you can see the typical length is about half to even way down further compared to standard glass. So it's kind of basically a chopped up version of standard glass, if you will. And then typical loading for that, 5 to 30%. It's not as common. You don't see it as often. What happens is it does help with your thermal and mechanical properties, and it does also shrink anisotropically, but not as much as standard glass. So that's kind of a bridge maybe where you are having issues with the shrinkage because you went to standard glass and it was too much. Maybe we find use in milled glass. Then you have long glass fiber, which is going to be standard loading, 35 to 60%, much longer length. So it goes all the way up to your 12 millimeter and then beyond. And so same thing, anisotropic shrink. This is great for stuff where you need pretty good boost in mechanical properties. And then lastly, we have carbon fibers. So you typically see that in the 5 to 40% range. The one thing to note here is because of the color of the carbon fiber, it is difficult to do it in certain colors. So typically we just sell the material in black because it's easier that way because it's already kind of a grayish color, grayish blackish color. So we just sell it in black. It makes it easiest. It is a little bit more expensive. The other thing that's unique about the carbon fiber is that it will impart some level of conductivity. And so that's another value if you're looking at certain materials, maybe an ESD range for performance or for properties, something that could be looked at as well. So aspect ratio, I brought it up quickly. So essentially aspect ratio, if you hear this term or someone says it when they're talking about glass fiber, it has to do with the fiber's length to its diameter. So glass fibers are cylindrical in shape. And so because of that, that's what aligns in the flow when you're molding it. And that's what also gives it its strength because it will line up in that direction, give it its strength. And then these quick pictures, they're a little, I would say a little blurry, if you will, but it does give you an idea. You can kind of see the milled glass is a little bit shorter than your standard glass compared to your long glass fiber. So again, aspect ratio, it's what causes the anisotropic shrink, but also the directional performance that you get out of the material. So just wanted to bring that up in case you hear that term and you were curious what that meant. So the next thing I want to talk about when we're talking about the aesthetics, so glass at this point is sounding pretty good. You get a good boost in mechanicals, you get a good boost in thermal. We are warning about the shrinkage difference. So as long as you kind of design for that and you're prepared for that, everything sounds great. You're like, this is wonderful. I'm getting everything I need out of this. The other thing to keep in mind is glass will end up on the surface. It will make the surface a little bit rougher and it will affect the appearance of the material. So if you look at this part, you can see over here on the left-hand side, this is a 30 glass PA66 grade. So you can see it's a little bit rougher. It's not as shiny, not as glossy compared to your unfilled 6.6. So you are going to see a difference in the way that it looks. So if you're looking at something where you're like, you know what, the aesthetics are absolutely important, it's going to be a huge deal breaker. It's going to be something that you might have to look at if you need to move to a glass filled grade because of the mechanical and thermal performance you get from it. The other thing to note here is I don't have a picture of mineral filled or filler filled material compared to the normal. It will affect it as well a little bit. It will not be as drastic as the fibers though. So just if it is an aesthetic thing and it's more important, maybe potentially the option for a filler could be used. So wanted to point that out. So next we'll talk about fillers a little bit. So we kind of talked about the different mineral ones and then the glass bead ones. Similar concept, I give kind of the size and the shape. So if you look at the form, it has more 2D form or sphere form. So it doesn't have that aspect ratio like your glass does. It's not a long fiber. But standard loading for these things, anywhere from 5 to 40% is really common that you'll see for these. Various different sizes, you can see there's actually quite a big range for some of them, depending on what you're looking to do or what you're putting it in potentially. And then relative cost, fairly inexpensive compared to each other, and then the glass bead a little bit more expensive. So glass bead essentially is taking this long cylindrical fiber and then just having them in little sphere-shaped beads instead, so you still get a little bit of the boost in performance without having to deal as much with the issue of the shrinkage. So fillers, as I mentioned, because they don't have that aspect ratio, they're more uniform and sphere or 2D in shape, you're not going to have that issue with the shrinkage. So what do those look like? These are kind of under a microscope, kind of what they look like. I just wanted to provide pictures here. So your mica, wollastonite, calcium carbonate, and talc minerals, these are what they look like. So we've kind of talked about, I said, hey, it affects the thermal properties, it affects the mechanical properties, it affects the shrinkage. What does that actually look like? Let's put some numbers to it and let me show you what that looks like. And then I have some graphs as well to kind of really show you the difference that you can achieve by using fibers and fillers. So for this study, I used fiber and filler in PA66. So your first one is the column for unfilled. So this should be your standard unfilled 66. Then we have a 13 glass, a 33 glass, and a 40% mineral to show the performance difference. So we talked about it improving the mechanical. So if you look at your tensile stress, you start at 81 and an unfilled, and you get all the way up to 205 if you're using 33 glass. Now, if you follow the pattern, 13 is an improvement, 33 is an improvement. If you add even more, it's going to be an improvement as well. So if you went up to a 50 glass or a 60 glass, again, continue to improve. And then the mineral, you can see it did improve it a little bit as well, but like we've mentioned, not as drastic as it would be as the glass. And then tensile strain, we talked about elongation taking a big dip when you add stuff to it. So you can see quite a dip there. And then your impact, your HDT, and your shrinkage. So I'm gonna leave this table here for you guys to review later at a later time when you open the PDF, but I wanna get into the visuals because it really shows the drastic difference when you're looking at it. So in this graph, you'll see the tensile strength or tensile stress, depending on the word you'd prefer to use for it. But you could see you go from an unfilled at 81 all the way up to a 205 at 33 glass. Again, add more glass, gets better, but you're looking at a 150% increase. So huge increase in your performance there if you're using a standard unfilled 6.6 and your application requires it to be a little bit stronger, a little bit more strength out of it. And then you take a hit here. If it's something where your elongation is important and it needs to be able to elongate just a little bit, you're going to start to lose that as soon as you add fiber. So just keep that in mind. It takes a huge dip, like a 90% decrease in nylon itself. You still get quite the decrease in your mineral, not as great. HDT, and we will talk about it as a rule of thumb. HDT is more greatly impacted when you add glass into semi-crystalline materials than amorphous. And we'll actually see that in graphs as well. I have an amorphous material to show the performance difference as well. But quite a big increase, over a 230% increase in your HDT performance, just moving to a 13 glass. And then shrinkage. This is the big one that I want to touch on. I kind of keep bringing it up because it's so important to understand. So if you look at your unfilled, you can see that it's about 2% standard across the board for 6.6 flow and cross flow. These versions here, what we're looking at is the flow versus cross flow. So you have your standard flow versus cross flow, and you could see that because of the shift and the difference and how it's not going to be uniform, that's where you start to see your anisotropic shrinkage because it's going to shrink differently. Now your mineral, not nearly as affected. Almost negligible at this point. So if you need something where it's going to shrink uniformly, like it kind of would unfilled, you'd look at mineral. This is the trade-off you have to make when you're getting that boost in performance mechanically. So this one we're to talk about PEI and fiber reinforcement. So this would be just unfilled versus 10, 20, 30%, just again, to give you an idea of the performance and the level of change. So you see here stuff like CLTE across the board, it decreased. Your tensile strength got better. Your HDT got a little bit better, but not a huge boost. And then your shrinkage. This is another point I want to make, and I will make as we get to the graphs, is that the shrinkage, when you're talking about amorphous, when they're filled, not as greatly affected because it's already not shrinking a ton compared to your semi-crystalline materials. So again, kind of what that looks like in a nice graph form. You go from 110 MPa all the way up to 175 with the added glass. Now, PEI by itself is already a fairly strong and stiff material. So adding the glass does improve it a little bit, but not as drastically because it's already a pretty strong material. And then your strain, again, big dip. So that's going to be something that if you can't dip, you lose that level of elongation, it's going to be a problem. Just want to keep driving that point home for everybody. HDT, little bit of a boost in performance. Again, we'll talk about it. It's not as large of an increase as you saw with the semi-crystalline material. And so, but you do get a little bit of a boost there. Now shrinkage, this is the big point I'd like to make. You could see that because the material already doesn't shrink a ton, you're talking unfilled's already at just 0.6%. It does decrease it just a little bit, but again, it stays fairly uniform even with the glass because it's already not shrinking a ton, so it's not drastically changing it as much. So again, another point to make. And then this one, I'm not going to go over each point, but I did want to put this in here. So your mineral filled materials are going to be typically propylene is a very common material that you're going to use mineral filler in. So I wanted to give you an idea of kind of what that looked like across different fillers. So you have your unfilled propylene compared to calcium carbonate filled, mica filled, and talc filled. So you will see a common thread here is that you do see an increase in the HDT performance a little bit of a boost. If you were to use glass, it would be quite a larger boost, as we mentioned. And so that is just a nice little visual for you guys to see that it is improving it a little bit. The other thing that would be here would be the shrinkage. It wouldn't shrink as much. So if that's an issue you're running into, maybe with your unfilled propylene and you've got an issue with it shrinking too much or not as uniform as maybe you'd like, mineral could potentially help with that. So another thing that it could aid. So things to consider. So I kind of brought this up here and there on some of these. So I do want to touch base and talk about them again. Anisotropic shrinkage, your differential shrinkage, most greatly going to be affected when you're looking at using fiber fillers in semi-crystalline materials, fiber reinforcement in semi-crystalline materials. Because of the differential in shrink, it tends to lead to warp. So I keep saying it's a problem, but what does that actually mean? What happens is because it wants to shrink more in one direction than the other, it tends to cause your parts to warp. If you had a flat part, maybe a disc or something, it would start to kind of do more of like a bowing up kind of thing where it would start to warp in that way. So if you're not prepared for it or it's not designed that way, it can be a shock when you find that, you start having parts that are warping and becoming a problem. There is a way you could potentially get around that. One would be obviously fillers. If you can lose that level of jump in performance and just use fillers, it would help. The other thing would be you could use a fiber and filler reinforced material. So that would be where you use some glass and mineral, because the mineral would it would stop from the directional lining up of the fibers. So you could potentially do that as well. It is an option. But just, again, I want to keep pointing that out because that's one of the downsides of using the fibers. Again, shrinkage more greatly affected in semi-crystalline materials because they are going to shrink more. And so the fibers start to limit that shrinkage in the flow direction because they kind of line up, get in the way. So a lot more affected than amorphous. The other thing that I want to point out, so this is kind of unique. So fibers are going to change the impact of the material. And so, but how it affects the material is different based on the performance of the material already. So if you take a really tough material like an unfilled PC, something that's got 10 plus IZOD type performance, and then you add glass to it, it's actually going to become more brittle and the performance is going to be decreased. That's why you don't typically see fiber in PC, because PC you're using because you're using it because it's clear, maybe because of the heat, but also probably because it's a very tough material. So adding glass to that is going to affect that. Now, if you take something that's already a brittle material like a polystyrene and you add fibers to it, it's actually going to show on paper a relative increase in toughness, if you will. So just keep that in mind. That's why we don't see it a lot. So when people ask for a glass-filled PC, we go, well, what are we trying to get here? Because we're just going to take away what makes PC, which is that it's really tough. And then lastly, the point I wanted to make about HDT is, so generally it's kind of dictated by what's called the glass transition temperature of the material. So that's going to be when the molecules are kind of able to start moving at that temperature. And so as you can imagine, as they're able to start moving, it's going to deflect, and that's where you get the HDT measurement. So with your amorphous materials really only having a TG as a thermal transition point, adding glass to it doesn't really raise the value too much, because it's, as soon as you get close to that TG, it's gonna fail regardless. Now your semi-crystalline materials, because they have two thermal transition points, your TG, which is where it starts to move a little bit, so you will actually see HDT there as a problem. But if you add glass to it, it gives it the stiffness and the structure to hold on. And so it actually will allow you to get a lot closer to the melting point, the TM of the material for a semi-crystalline. So that was apparent if we go back and you look at the graphs for the polyamide, you saw that it jumped drastically from an unfilled to a glass filled, and that's why. And then with the PEI, the jump was not as great. It was a little bit of a jump, but not as great of a jump in performance. And then lastly, just a couple applications that you're going to see glass filled or mineral filled products. So glass filled polyamide, I talked about this one a lot. There are plenty of other glass filled materials. It just happens to be a very common one. So that's why I used it for the majority of the presentation. So your glass filled polyamide materials, you're going to see them in stuff like airbag modules, brackets. We're going to need that structural component to it. It needs to hold a good strength and stiffness. Firearm components, same thing. It needs to hold that level of structure. And then stuff like your mineral filled propylenes, the air filter frames, maybe a fuse box, flower pots, needs a little bit of structure to it, but not as much as you would need out of the glass. So for that, and those are just a couple of the applications. There's plenty of other applications out there, as I'm sure you're well aware, because I'm sure a lot of them are being used. And the other thing I did want to point out that I realized I didn't really put time into it and a slide would be glass fibers. They are abrasive in nature. And so that's the other downside as well, is that they actually will tear up your equipment a lot quicker. And so if you need it and you absolutely need the performance and the boost, absolutely use the glass reinforced materials. But if you don't need it, it's one less thing to tear up your equipment and get it to wear quicker. So I did want to bring that up real quick. I realized I didn't have a slide for it, but I did want to make that point that the glass fiber is very abrasive and it will attack your equipment a lot quicker than just, your standard unfilled materials. And with that, that's all I had for this presentation. But at this point, I'm going to kind of open it up. I don't know if there's questions or not, but I'll let Sherry kind of take back over. And if you guys have some questions, feel free to ask. And then again, as she mentioned, if we don't get to it, shoot me a note, give me a call. We can discuss any further questions you might have.
Awesome. Thank you, Andrea, for your comprehensive presentation once again. At this time, like Andrea said, if you have any questions, please type them in the questions section or raise your hand and I will unmute your microphone and you can just ask us your question out loud. We have Andy Conti, Technical Development Engineer, who has been with Chase Plastics for 18 years, on hand to assist Andrea with questions today. But while he's reading those real quick, once again, if you'd like to download the handouts, now would be the time to do so before the webinar ends. Andrea's presentation will not be emailed to you. So if you'd like a copy, please download it from the handout section now. As a reminder, as you type your questions, please complete the survey at the end of this webinar. Your responses will help shape future Chase the Knowledge webinars, and we welcome your feedback. Also, like I said earlier, please be sure to check out our new blog page at chaseplastics.com/blogs. And you can access past webinar recordings and future webinar announcements at chaseplastics.com/webinars. And if you'd like to have a custom Chase the Knowledge topic presented to your organization, please reach out to Andrea or myself. And with that, I will hand it over to Andy, because Andy, it looks like we have a couple of questions.
Yes, we do. I'll start right from the top. Craig Reski asks, how does carbon fiber compare to glass when it comes to machine and tool damage? Carbon fiber is not nearly as abrasive as glass fiber is. So from that aspect, I would not expect it to be as bad. However, still compared to an unfilled, you'll probably see some increase there. Let's see. Mindy asks, are there any post-processing techniques to add additives, fillers to a material? Thinking something along the lines of hygroscopic properties. No, I'm not really a post-processing. I guess I'm not exactly sure when you're thinking of the hygroscopic. Are you thinking about something to reduce the water pickup, say in a nylon, that would probably be more affected by the environment, but not really something that you can do post-processing. Mindy also asked another question: are concentrates for fillers something that are available similar to colorants? I've seen some people have concentrates of some talcs and all. I generally would be a little not endorsing of them, and the only reason for that is that to have a concentrate like that, you know, you're sort of depending on your injection molding machine now to distribute it, and really a molding machine isn't designed to give you that kind of dispersion. You know, with that said, you know, there are times, like for instance, it's very common to see things like a salt and pepper blend of two materials. Say if you're trying to adjust the glass loading, you've got a 33% glass loading, you want to cut it down to around 15 or 16, you cut it with you know, half of the virgin material. That does generally work. You'll generally get at least a good enough dispersion there. But like I said, you know, trying though to disperse a mineral, a lot of times with mineral, the challenge you have is that you not only want to disperse it, but you need to distribute it too. And here we're talking at very, very fine or very, very small sizes. And as I said, for that, an injection molding machine really won't do a good job. William asks, looking for an extrusion grade with minimal glass, 10 to 15% for improved mechanical properties. That generally would be something that you'd probably need to go to a custom compounder for. They do exist. Again, the you know, adding glass fibers here, I'd say you're probably going to see more of an increase in stiffness. Unfortunately, when you're extruding glass fiber, you tend to break it up, so you typically won't see the strength that you see on a data sheet for an injection molded part, but you can see an increase in stiffness. Eric asks, what are the differences between the different mineral fillers? Well, I mean, again, the primary differences are their aspect ratio. Things like talc and mica have a little bit of reinforcing properties because they do have some aspect ratio, whereas something like calcium carbonate or glass beads, because they really don't have an aspect ratio there, you're not really going to see that many difference in terms of the property improvement. Ron was asking, where is the handout section? I believe that is further down. It should be right underneath the questions area. Okay. Bill here was, William was asking, okay, currently evaluating a PETG. I believe that's off your 10 to 15% extrusion question further on up. So again, going to a custom compounder would be the direction to go. William asks, are there shortages of fillers that affect the availability of a specific resin? Right now, I'm not aware of any shortages on the mineral side. Certainly glass fiber is having supply issues. The only thing sort of from a, and it's not really a filler as much as an additive would be, I know that FR ingredients have also been tight for many grades. Rod asks, milled glass, are there different grades there, technical grades of milled glass? No, again, milled glass is typically used, I mean, there are different grades, certainly different polymers. There's an optimal diameter. So you can't necessarily use the same glass in every different material. So I guess from that aspect, yeah, there might be some differences, although typically milled glass does not have sizing on it. So you don't typically see as much difference in the milled glass as you do in the regular glass fibers. Let's see. Craig asks, what filler is the most cost effective? Well, again, from the point of view of fillers, a lot of times can be used to replace resin. Really, here it really depends a lot more on the resin you're putting it in. Give you an example: a glass reinforced polyether imide or a glass reinforced peak is certainly going to be less expensive than the unfilled product. That's because the glass fiber, relatively speaking, is less expensive than the resin it's replacing. On the other hand, when you're talking in the commodity materials, like I said, really the only one that I'm really aware of, when we're thinking of cost reduction, would be going with, say, like a calcium carbonate in propylene. Calcium carbonate and PVC, I know, also can reduce cost. However, you always have to balance any reduction in the price per pound. It is making it heavier, so you really need to look at the relationship in terms of dollars per cubic inch.
The other thing too I would add to that would be similar concept in TPEs. They have a high density and low density TPE options where they will use filler in it to get it to the higher density, if you will, but you're replacing some of the TPE with the filler, and there's the cost advantage there.
Okay. Mindy asked, if adding multiple fillers to a material, does the concentration of each need to be reduced to preserve the base resin properties? What is the total limit? I guess it really depends on what you're trying to achieve. The reason I say this is that there are cases, if you're trying to get a very heavy material, you can actually put in things like powdered tungsten or powdered steel into products. These can be added at levels all the way up to 70, 80% by weight. What's more important is really the amount of volume that they take up. Remember, if you've got something that you're adding that's very heavy, you can add a lot of it by weight. It won't take up much volume. A rule I always try to say, like I said, you can try to convert it into a volume percent. There are techniques that you can mathematically do that. And then I'd say probably, for safety's sake, I probably wouldn't want to have less than 65% resin by volume. And again, like I said, that typically translates for most fillers. Most fillers, I'd say that's usually around 40%. Most of the mineral fillers by weight are there. Again, once you start going beyond that, you can run into problems. Glass is, you can actually get all the way up to 60% by weight. But again, if you look at that, glass is still heavier than the base resin it's replacing. So it still has, there's still more resin by volume there to hold the compound together.
What I would add to that just a little bit, so the part of the question was, while still maintaining the base materials properties. I mean, ideally what you're doing is you're adding these things to it because you're trying to effectively change a property or properties to achieve something. And so we're adding it because we want to make a change. And then the other thing is not the property that you're maintaining. It's just you gotta make sure you have enough polymer there to actually process it. If you get too much in there, it's that the part of it that actually flows and processes is overtaken by what you're adding to it. So adding to what Andy said, we keep it at a certain level because we got to make sure that we can actually process the material at that point.
Mindy asks, are there new classes of fillers in development that are not yet available on the market? I'm not an expert in what the filler guys are coming out with. I know certainly probably the only thing I could say there that we really didn't touch on here, nano fillers, things that are very, very small. That's always an area of great development. There have been applications, I'd say, over the last 20 years, although typically there's still an issue with those in terms of getting the proper dispersion. It's very difficult to get consistent properties batch to batch on those, and I think that's what's holding it back. Let's see. William asks, any fillers you can add to a glass-filled resin to help reduce some warpage? Yes, certainly, like I said, mixes of both glass fiber and milled fiber. Glass fiber and glass beads can typically do that, as well as glass mineral loadings. And typically, like I said, I'd say probably one of the most common of these is is adding glass and mineral and things like nylon. You'll find many manufacturers, offer something that they'll call their 40% glass mineral. This is typically higher in mineral, about 25% mineral and about 15 glass. The reason they do that is they want to put in more mineral to help break up that orientation. But yes, glass minerals mixes would probably be the most common way to do that. Craig asks, do any of the fillers help or hurt with the weatherability of the plastic that it is in? Most of the time, I put it this way: fillers by eliminating resin, yeah, they probably can help it. Weatherability occurs right on the surface. The challenge, though, you're really going to have is still bonding the filler to the resin. So in other words, okay, an example. I know that things like TiO2, titanium dioxide, even though it's more of a pigment, is very useful for improving the weatherability of PVC because it tends to reflect light and scatter light. Really, like I said, but typically I would say you're really looking probably more at pigmentation and additives, specific antioxidants, UV absorbers, things along those lines, as opposed to fillers to really get that job done. There might be some effect, but again, those aren't going to be the fillers aren't going to be the heavy lifter for it.
Okay, I'm not seeing any more questions or any hands raised. So if you still have a question, please raise your hand or put it in the question section. But we would like to thank you all for taking time out of your busy schedules to attend this Chase the Knowledge webinar, and we hope that it was an informative and great return on the investment of your time today. If you have any technical questions that did not get answered today, feel free to reach out to Andrea or Andy directly. Andrea's information is posted right there on your screen. And again, thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar. Bye-bye.